Hello everyone. I'm going to be talking about inductors. And so inductors are passive devices like capacitors and resistors. And like capacitors, they can store energy. However, they store energy in the form of a magnetic field, whereas capacitors were storing energy in the form of an electric field. Okay, so inductors can take energy or store energy from a circuit and deliver energy back into a circuit, okay? And that's done through the magnetic field. So the way inductors are constructed is that they are typically a wire that's wrapped in a coil, okay? And in the center of that coil is some sort of core. So I'll explain it in terms of the symbol. So we have our symbol here of a inductor, okay? And so what would happen is we would have, let's say, current flowing in the inductor, so that would be some I, and then the current would go around in this coil, and a magnetic field would develop around the coil like so, that you've probably seen in physics, okay? So that's the magnetic field. Now, in the center of that coil, there can be just plain old air, okay, and that would be called an air core inductor, or it can have some sort of ferromagnetic material like some ferrite core. So that could look, something like this. It's some solid piece of ferromagnetic material inside the center of that coil, and what that does is it intensifies the magnetic field, so it effectively increases the inductance of the inductor, okay? And it has some other features that are a little bit drawbacks, but those are the two basic ways of making an inductor with an air core or a ferromagnetic core. Over here on the side, we have a couple of examples of inductors. So the one on the top is an inductor that's in kind of like a straight line, like we've got our symbol, and that's something that we use in the lab, okay? And you can see the value of it is 100 millihenries. Now the one on the bottom, this is an inductor in the form of a loop or a coil, okay? So it's wrapped up in a spiral around it, and both of those inductors have cores inside of them. And the bottom one is most likely what's called a choke, like an RF choke, like a high frequency choke, because it reduces high frequency signals and allows low frequency signals to pass, which is the general property of inductors anyway. So let's get into it a little bit. So the current voltage relationship using the passive reference convention is like this, and we have a basic equation that describes or relates the current to the voltage for an inductor, and that is the voltage is equal to the inductance times the change in current with respect to time. This equation is also written V is equal to L di dt. And you can see that there's some relationship you can see some relationship to capacitors, right? I is equal to C dV dt, right? So this is the form for the inductors. Okay, and L, of course, is the parameter for inductance, and the units are in henries, so it's H, okay, like 5 henries or 100 millihenries as we saw in the previous example. Okay, so now let's think of this equation a little bit, okay? V is equal to L di dt. So if we have current flowing through the inductor, and let's say it's a constant current, okay? So let's say it's like 5 amps, so that I of t is equal to 5 amps. The di dt is going to be 0 because the current is a constant, right? The derivative of a constant is 0. So then what happens? The voltage across the inductor is going to drop to 0, okay? So then where do we see that? So we have V is equal to L di dt, and then if di dt is equal to 0, well, that whole expression goes to 0. So in this case, the inductor behaves as a wire, or equivalently as a short circuit, okay? So then let's maybe make a little annotation on our circuit over here. So let's imagine we had a current source and there was a constant current, let's say 5 amps, okay? So what is the voltage VLT, okay? What's the voltage across that inductor? Well, according to what we just analyzed, right, di dt is equal to 0, so the voltage is going to have to be equal to 0. So this voltage, let's say, is going to be 0 volts, okay? So that's what that means. Okay, let's continue. Okay, so now there's another observation that we can make for this equation V is equal to L di dt, which describes the inductance behavior, and the current cannot change instantaneously in an inductor, okay? So then imagine if our current was changing, let's say instantaneously. Let's say we're trying to go from 2 amps and just step up to 10 amps instantly. Or maybe even more realistically, let's say we had 5 amps flowing through the inductor, and then we open the circuit to break the circuit. Let's say there is a switch, and then what would happen? If you open a switch, the circuit is broken and there shouldn't be any current flowing, okay? So what happens is very interesting. So if you try to change di dt, so if it's going up, if you increase it, then you can see that, of course, V across the inductor is going to increase as well, okay? And it's going to increase so much proportionate to the change in the current, and eventually it will rise so quickly that it will create a spark, and then the whatever current will flow through that spark and complete the circuit, okay? So it can be a little bit tricky to work with inductors. Okay. So now let's develop the relationship for the inductor current, knowing what we know about V is equal to L di dt. Let's have an expression I of t is equal to something related to voltage, of course. Okay, so then if we multiply by the differential of time, dt, so we're going to get V dt times L di dt, okay? And then if we integrate both sides, then we get an expression like this, and we're going to use some arbitrary lower limit, some t naught, that's the initial time, okay? And the converse, right, we have to take the integral with respect to time on the other side. It's a function of current rather, and so it's going to be the initial current I of t naught, okay? And we're doing the change of variable that we saw when we talked about the capacitors, okay? That's just to help us with our calculus. And then that's going to resolve itself to L times I of t minus the initial current I of t naught. And then, so then we, if we solve for I of t, so we're just going to rearrange that equation, we get the equation on the bottom. Okay, so that's a fundamental equation, and let's see what that means, okay? So we have this I of t naught, that is the initial inductor current, okay, for what we're solving for. And then this part here, this is how the current is building up in the inductor due to the voltage, okay? It's due to the voltage. So this is the current buildup. And, of course, the most important thing is the total current. That's the thing that we're solving for. So that's the inductor current, okay? I of t. So that is the current in an inductor. And this expression is often written with this T naught being 0. Okay? So that can be maybe a more simplified way of thinking about that equation, but depending on the circumstances that you're using it, it's the initial time. And if you recall in the capacitor waveforms, in some of the cases, t was not equal to 0 as an initial time. Okay, so now let us look into the power relationships of the inductor. Okay, and we have this up here just as a reference. Okay, so then power is equal to voltage times current. Okay, this is always going to be true, so it's a super handy relationship. And then let's see how we're going to interpret that. So power is equal to voltage times current, and here we have the expression for voltage, okay, times the current. Okay, so that's a pretty straightforward one. Okay, we've just plunked in this. Okay, and then we have another expression where we have, power is equal to voltage times current, and then, so we have voltage here, okay, and then this term is the current, okay, and that's a relationship that we found just a little bit earlier, okay, so it's still voltage times current, okay. So that's a very useful relationship. So now let's find the energy, okay? So now we're going to look at the energy in an inductor, and we know the relationships, power is equal to the change in energy with respect to time, and it's V times I, and then this is our expression, V times I in a more expanded form. And then if we multiply by the differential of time, then we're going to get this down here and this just by a little bit of rearranging over here. Okay, it's just a little bit of rearranging. Okay, and then what we got, if we integrate that result, okay, we're going to integrate both sides, okay, and then we end up with a very, very useful equation for the energy of the inductor, energy being 1/2 L I squared, okay? And remember, the energy in a capacitor was 1/2 CV squared. For an inductor, it's 1/2 Li squared, okay? Very useful relationship. And then we could write it in a more simplified form like this. Energy is equal to 1/2 Li squared, okay? It's the same thing. So now, let us look at how inductors add in series and in parallel. So first we're going to do series, okay? So we're just going to develop the relationship. So I'm just going to show you how to develop the relationship. So if we consider a circuit with a current source and 3 series inductors of different values, L1, L2, and L3, we can say that there is some voltage across the source, and then each inductor has their own V1, V2, and V3. Okay? So then we can write a KVL equation for that loop, and so it's just going to be V is equal to V1 plus V2 plus V3. Okay? That's pretty straightforward. And then if we sub in V is equal to L di dt, we get the below. So this is V1, V2, V3. Okay? And so what are we doing here? Of course, each term has its own inductance value, okay, for each voltage, because there's different inductors, so they're going to have different voltages, right? But what's interesting is that they share a common di dt. And the reason why they share a common di dt is because this I is the same throughout the entire circuit, so di dt is going to be the same. Okay? So then, if we factor out di dt, we get L1 plus L2 plus L3 times di dt, and if we just specify L1 plus L2 plus L3 as L equivalent, then we can get the relationship L equivalent is equal to L1 plus L2 plus whatever how many inductors you have in series. You're going to add them all up. And so what we can say is that inductors in series add like series resistors, okay? So that's different than how we saw the capacitance, right? So inductors behave like resistors. So now you've done enough to, you've done this a few times. So now what would happen if you had n equal valued inductors in series, okay? What would be the total equivalent inductance, right? So they're all in series, they're all the same value, and you have n of them, right? So let's say n is 100, whatever. So then the total inductance would be n times L, or the inductance, right? So if it was 100 inductors, it would be 100 times the inductance value of the individual inductors. Okay. So then we've done series, so let us do parallel. So for parallel inductors, imagine we have 3 parallel inductors with a voltage source, and then you're going to have some current I flowing in, and you're going to have an I1 going in, I2, and I3 in each branch. So then, using a KCL equation, we're going to have I is equal to L1 plus L2 plus L3. Okay, if we sub in the integral relationship for current that we found earlier, right? So for this I, we got this. For this I, we got this. For this I, we got this. Okay? So then we see that the voltages are the same, right? Okay? The voltages are the same, right? Or the integral is the same, which is based on the voltage. And that's because the voltage is the same for every inductor because they're in parallel, okay? So then we can factor out the integral and then take out the 1 over L1 plus 1 over L2 plus 1 over L3, okay? And then this is what's factored out. So then we can call that sum 1 over L equivalent, just like what we did for back when we were doing series capacitors, right? And then we can say that the equation for parallel inductors is 1 over L equivalent being equal to 1 over L1 plus 1 over L2 plus 1 over however many inductors we have in parallel until we get to the last one, okay? So that's the same form as for parallel resistors, okay? And if we had n equal valued parallel inductors, of course, the equivalent would be just like for resistors, it would be L divided by N, okay? Okay, that's it for an introduction to inductors, and next I will do an example doing the inductor waveforms.